Hi everyone. This video is going to be on hygroscopic substances, or we call them hydrates, some of them. And one of the biggest things I want to say is that this is the last part of the unit, so people tend to actually write this off and really put their focus on like all the mole calculations and stuff. But this is also going to appear. This is just as important. So if you don't have something handy to write notes or something, I would just like pause real quick and do what you need to do to grab stuff. But this is just as important, pretty much. So just keep that in mind. But okay, so hygroscopic substances. Um, if you look at these packets here, you've probably seen these before if you buy some new clothes or buy some new shoes or anything that kind of needs to be kept fresh might have these in there. And these are examples, these are called desiccants. They're examples of hygroscopic substances. And the reason why they're there and what they do is they absorb the moisture from the air. So when your shoes or your things are coming to you, they may come and in the passage of their travel, they may come across humid environments. And so these packets are in there to absorb all that humidity and keep everything dry and crisp and like it's brand new pretty much. So that's the purpose of them. So that's what desiccants are for drying. They're drying agents pretty much. And that's why they're there, to keep everything dry. And so you may have heard of someone being in the situation, or you may have been in the situation yourself where you get your cell phone wet or your electronics wet, and then you put it in rice to help dry it out, right? Rice doesn't work exactly like this. This is actually a better substitute than rice if you have some of these substances, and because what they do is you put them in there with the rice, and they don't even have to. I mean, you put them in there with the technology, and they don't even have to be touching the technology because they're literally sucking the water that's in the air. You may not really be aware of it because it doesn't affect us all that often, but there's always a certain amount of humidity in the air. Some days it's like really humid, right? And you're like, oh, I'm feeling it, especially if you're down in like Florida or something. But to some extent, there is always water vapor within the air. It's just some days it's really bad, but there's always water vapor there. And so if these are left out, right, in an unsealed thing, they're going to go ahead and absorb that moisture that's in the air. That's what they do. So to have that quality, to do that is to be hygroscopic. That's the adjective. And desiccants is sort of the noun form. And another noun form are called hydrates. So there are actually specific chemicals that do this, and they're referred to as hydrates. And this is sort of really weird. So hopefully I'll get to show you an example of this in class, but gonna have to do a little bit of imagining here. Um, hydrates themselves are ionic compounds, right, like we've been talking about before, but they have water molecules actually bound to their chemical structure. So the weird thing is that they have water inherently in their structure. So if you touch them, they're not actually wet. Now, don't even go there with this water wet stuff. That's a separate conversation. But these substances, because the water is actually sort of like attached to the ionic compound, it's not actually wet. Like it doesn't look or feel wet or anything like that. It's not actually wet. It's got the water like bonded within it. And that's what makes it a special hydrate chemical. And yeah, so that's a part of it pretty much. So when it doesn't have water bonded to it, it's called the anhydrate form, or like so that's like the noun is the anhydrate. The adjective is to say it's anhydrous, or it's like an, right, is without, and hydrate is water. So the anhydrous form means no water in there. And at that point, it's going to actually typically look different. So here's an example down here. On the left, if you look at these blue crystals, this is the hydrate form. And again, if you look at it, it's not wet. Like you can tell there's no sheen to it that would say like, oh, there's water in there kind of thing. Like it's not, when something is wet, that means it's a mixture of that thing and water. Hydrates are an actual chemical. They're not like a mixture of a couple of things. Water is part of it. It's a pure substance. That's what's so weird to imagine. And on the right here is the anhydrous form, but these are literally the same chemical. That's what's so interesting. So these are the same chemical, and on the right is the one that has water heated out of it. So pretty much what's happened is that someone took the blue crystals and they exposed them to heat, like on the Bunsen burner or on a hot plate or something, and they get hot enough that the water will leave the structure. And when that happens, it'll typically change color like this one. And the anhydrous form is the one that actually does absorb the moisture from the air because it can go both ways. Let me actually just go to the next one and show you. here is this sort of like reversible process. So on the left, we got the hydrated version, the hydrate. This is copper 2 sulfate with the hydrate form. And then on the right, we've got the anhydrous form. This is after the water's been heated out. But let me just show you a visual here, right? So here's the water being heated out of it. Actually, this is water being put back in. Now they're going to be, this is a flame. They're heating the water out of it. It doesn't get, I think, all of it out. Actually, yeah, they got all of it out. So this is the anhydrous form. And then to reverse it, all that they do is they actually just drop some water in there. And now it's the hydrate form again. And there is some extra water in there, so yes, this actually looks wet, but not as much water as there should be if it wasn't part of the structure itself, right? So yeah, in this particular version, it's blue when it's the hydrated form, and it's a white powder when it's the anhydrous form when the water has left. So this is an important concept to know, is that that's what hydrates do. If you heat the hydrated form, the water will leave and it'll change color. There's another one that that switches between like an interesting purple if it's a hydrated form, and then like a red color if it's I think it's gonna be red if it's not hydrated. But we stopped using that because that's like a carcinogen chemical that we found out later, that scientists found out later. But but yeah, so if you take the hydrate form and you heat it up, it will actually lose mass because water is leaving the chemical. And so water is vaporizing, it's going out into the air, and therefore your hydrate will lose mass because of that. By the same token, if you have the anhydrous form and you just leave it out in the classroom or even anywhere pretty much, it's actually going to gain mass because it's going to be gradually absorbing moisture from the air. And if you were to look at it, it would gradually start to turn blue because it's actually slowly absorbing that moisture from the air. And again, there's always moisture in the air. It doesn't mean it's a hot, humid day. If you ever check like weather reports, they're like, it's this humidity and this heat. There's always moisture there. In fact, if you think about during the winter, maybe when the heat's on is when there's less moisture, and that's when things start to get really dry. So moisture is actually good. We like to have moisture. There's some moisture always in the air. But yeah, so if you have the hydrated form and you heat it up, it will lose mass. As the water leaves it, it'll start to change color because literally the water's leaving it. And then if you take the anhydrous form of it, it will gradually start to turn blue and gain mass as water is incorporated back into its chemical structure. Okay, but let's take a look at. We also need to know how to name these formulas and go from the names to the formula. So go back and forth from names to formula, formula to name. Nice thing is it's not all that challenging, to be honest. So the formula as a hydrate is written as the ionic compound, right? So we already did ionic compounds, followed by a dot and then the number of water molecules. Now this dot in math means multiplication. It does not mean that here. Like, do not think about that at all here. This dot does not mean at all multiplication. It's just some weird format they chose. What it means in this case, for example, is that for every formula of calcium chloride, there are 2 water molecules attached within the structure. That's all that it means. Nothing to do mathematically with multiplication. To name the hydrate, you take the name of the ionic compound, followed by a prefix, so we're kind of mixing the naming rules here, followed by a prefix to indicate the number of water molecules, then by the word hydrate. So for example, this one is called calcium chloride dihydrate, right? So instead of saying water, we're saying hydrate. That's the word. Calcium chloride dihydrate. So that's pretty much how that works. Okay. So let's go from formula to name. If you look at your periodic table, this is called magnesium, of course. This is called sulfate. So this is called magnesium sulfate hepta, right? Because hepta is the prefix for 7, hydrate. Magnesium sulfate heptahydrate. This one is copper varies actually, so we have to actually use the Roman numeral in the name. So this is copper Roman numeral 2 sulfate pentahydrate. So I definitely recommend you pause and like practice saying that, not just writing these things out, but even just getting your tongue into the muscle memory of saying this helps a lot in terms of your preparation, your studying. But all right, so these other one, to get this pretty much, so this is sodium carbonate decahydrate. So let me just see if I can draw this in real quick. So we know sodium is Na plus, sorry for the atrocious handwriting with this pen, and carbonate on your polyatomics is C capital O3, 2 minus. Holy cow, hang on a second, let me see if I can get something, there we go. Okay, so we put them together, it's going to be Na2CO3. Man, if you thought my classroom handwriting was bad, holy cow. Okay, but we got to keep it going. It's decahydrate, so dot 10 at H2O. Again, not multiplication. That's not what that means. Okay, so that's for that one. Cobalt's a 2 plus, chloride is a 1 minus, so this would be C little o, Cl 2, because they're telling us cobalt's 2 plus and Cl is 1 minus, dot hexahydrate, so that's 6, hexa 6. Remember you get these on the back of your periodic table. H2O. So that's how you do it pretty much. Again, it's not all that different, it's just new, that's all. Let me erase all these if I can, erase all, there we go. Very last thing about this. When you're doing the molar masses of this, what you pretty much want to know is that all that you're doing, right, there's no multiplication in this process. That dot does not mean multiplication, so forget that stuff. Do the molar mass of the ionic portion of the compound like you would normally, right? That part's fine. The dot, instead of think of it as being like a plus 7 water molecules. So, I mean, to save yourself some time, I would just remember that water is 18.02. You can always add it back up if you want to. But yeah, so this one's mass is the mass of magnesium sulfate. I got this from the periodic table. Plus 7 waters equals the mass of 1 mole here. This is the molar mass of magnesium sulfate heptahydrate. This one is the mass of CuSO4 plus 5 times the water. So this is the mass of copper 2 sulfate pentahydrate, and that's this one. These are the examples we did in the last slide. All right, this one is just the mass of Na2CO3 plus 10 waters, so 10 times that equals this number. So this is for sodium carbonate decahydrate. And then finally, this is the mass of this one, so you take CO, Cl2 like you would normally, plus 6 water molecules equals that for cobalt 2 chloride hexahydrate. Okay, so again, that's this is going to be just as important. Thanks for watching, and feel free to let me know if you have any questions.